Okay, so I think I kind of briefly talked about this the other day. In Unit 1, we're going to talk all about diversity of matter chemical bonding, so how things bond together, what that looks like, what are some properties of those things. Yeah, a lot about properties, a lot of theory. And I don't really name lessons. I just call lesson 1 or 2. We just kind of divide it into material. Each one will have its own little subtopic, I guess, or heading kind of thing as we go. All right. So Unit 1, Lesson 1. Just a little bit of review, a few things at the beginning here, and I know you've seen this before probably, but we're going to talk just a little bit about physical changes and chemical changes. Physical changes, of course, a change, and you probably don't even need this. If you just write this down, that's probably fine, but a physical change is a change in matter or structure in which there's no new substance being formed. Things that indicate a chemical change has taken place, for example, are, like I said, we can't form anything new. So things like change of states is a prime example of a physical change in states. Water as ice and as solid, liquid, and as a gas. That's a physical change. Okay, water's still water, but we're just changing states. That's basically what a physical change is states. That's going to be important for us in Unit 1 because we're going to talk about things like melting points and boiling points for us, how things combine together, how strong do they hold together, how much energy does it take to break some of those bonds in order to change states, solid, liquid, gas. Okay, so that's what we're talking about there. If you melt an ice cube, you still have water. Okay, we have H2O, we have H2O. Breaking a pane of glass, ripping a sheet of paper, it's still paper. All right. Okay, so those are physical changes. We're not making anything new. Obviously, with a chemical change, we are looking to make something new. That's the whole purpose of, in a lot of cases, chemistry. We want to make something new. We want to chemically change it. That's a change in matter where which one or more new substances is formed. Not quite often, but a lot of the times we'll get 2, maybe 3 products. Sometimes when we combine different things together. Burning a piece of paper, so that's an example of combustion. Okay. Rusting of metal. So do you take iron plus oxygen plus water? Okay, we get some iron hydroxide, iron 3 hydroxide, which is rust. Okay. No. So, am I recording? Let's see. Oh yeah. Yeah, so chemical change, obviously, where we're trying to make something new, right? You get a little fender bender or whatever, and the metal gets exposed. Well, that's the iron. That's part of steel, of course, or whatever. They don't really make cars with steel. I don't know why I'm recording this, but they don't really make cars with steel anymore. Well, they do, but they don't. You know what I mean? It's all plastic now. Saturn, you could jump on the doors and they'd bounce back, and they don't make Saturns anymore. I don't know, but anyway, yeah. But if you have a little fender bender and you get a little ding, like my truck, I had a few little incidences, no accidents really, but just some scrapes and stuff, and it starts to rust right away because the iron reacts with the oxygen and the water, and it creates rust, right? We're not going to copy this top part, okay? We're just going to skip right down to here because that's all good. So I'd say let's copy this bottom part here. Just give me 1 second though here. Every chemical reaction involves at least one new substance being formed. The products of a chemical reaction always have different properties from the initial reactants. Here's some clues that indicate a chemical change is taking place. That's the important part here. So clues that indicate a chemical change is taking place. And there they are there. I'll let you guys copy while I'm. So energy in the form of heat or light is either absorbed or released. So that's a clue. Of course, we have names for that, absorbed and released. What are those called? What do we talk about in chemistry? What are those? I'm going to just point probably. Anyone? What's the term for energy released, energy absorbed? Oh, come on. Yep. Doesn't matter. Yeah, endothermic and exothermic. Endothermic takes energy in, right? Those are things like cold packs and ice packs. You get, it takes energy from its surroundings basically in order for it to happen. Exothermic is like, your barbecue gives off energy, right? You burn it and heat is a product of that, okay? So energy can be absorbed or released, and it can be in the form of light as well. Okay, when we excite electrons, they jump up to the next level, and when they fall back down, they emit a certain light. Okay, so that could be a color change takes place. So quite often we'll see different colors that are start to form. Sometimes that actually goes with this one. A new solid is formed as well. So when we mix two solutions together, sometimes we get what's known as a precipitate. Okay, a solid that's formed. We have a solubility chart for that, yes, and we can kind of predict if a solid's going to form or not based on that. And we'll review that, of course, when the time comes. And sometimes those solids have a new pretty color, and that's one of our labs eventually, hopefully, down the road here. And then a new gas is produced as well. Okay, so quite often you'll see a gas that's formed. If it's in a solution, like for example, if you take zinc, okay, a chunk of zinc, or even magnesium, strip of magnesium, and you put it into some hydrochloric acid, you will get hydrogen bubbles, right? Which are part of the solution there. You'll see the hydrogen bubbles form, and that could be in the form of bubbles in a solution. Odors are another thing that you could use for clue that a chemical change is taking place. So odors are another option as well. Okay. All right. We'll just briefly take these as. Am I recording? Oh yeah, good. We'll just briefly take these as well, and then I think we're pretty much done with this first one here. But a qualitative observation describes the qualities of matter or changes in matter. So things like changing color, odor, or physical state. Quantitative involves quantities. Okay, so some kind of amount in change. All right, so qualitative observation, like I said, are qualities, matters of change, changes in color, odor, physical state. You know, those are something that we would see with somebody like quantitative obviously involves amount of change in some way, shape, or form. So it could be the concentration or the mass or something along that line. Okay. I think we will copy this. I don't think we need to copy this, of course, but you know what? Do we need? Yeah, let's, I guess, don't worry about that, but let's just copy that down. All matter is made up of atoms, of course, we know that, I think. The different types of atoms that exist are known as elements, and they can be found in the periodic table. Copy this. But matter, of course, is made up of pure substances and mixtures. We're going to kind of focus, we're going to talk about a little bit about solutions eventually. You don't have to worry about this, but mostly we focus on elements and compounds, and we will talk about some solutions as well. Okay. Let us do this. We're going to copy down. Yeah, yeah, we can copy this, I think. So let's copy down the element part here. A pure substance is made up of only one type of atom. Each element has its own unique set of properties. And we'll kind of stop here right now, but elements cannot be broken down or broken apart by chemical reactions. Okay, I was just talking about nuclear reactions. That's a little different. We're Chem 20. We'll stick with maybe chemical stuff. Okay, that's a joke. We don't want to do nuclear chemistry yet. So elements, each set of elements has its own unique properties, cannot be broken down by chemical reactions. You can use nuclear reactions to break them apart or build them up in some cases. We're not going to, don't worry about copying that. Don't worry about, I shouldn't do that. Here, let's do this. There we go, problem solved. True, most, we probably should copy that. But let me talk about that real quick here. Most elements exist as elements by themselves. And what that means is basically this. If I'm walking down the street on my way to 7-Eleven at lunchtime, and you're walking down the street and you're like, hey, look, it's carbon atom. Okay, for the people at home, it's not going well. Okay. You can't see atoms. That's why it's funny. Or you're like, hey, look, magnesium atom. I'm going to use this joke again, okay? So just get used to laughing. Just humor me. Then you're walking, magnesium atom. You would find one by itself, okay? So most elements exist like that. You could find individual atoms. Some do not. Some chances are you finding one by themselves are probably not likely. For example, you're walking down the street and you're like, you look up in the air and you're like, hey, look, it's oxygen. Well, oxygen comes in twos usually. Okay, two atoms joined together to kind of form this what we call a molecular element. Do you guys remember the molecular elements from last year? Some teachers will use this term like Hofbrinkel, right? I have my own, which is really catchy, right? Yes. Uh, and I'll show you that eventually. It's funny. I use a little acronym. I think it's called. I'm not an English teacher, so I don't really know, but I use a little acronym, and that's when you take the first thing and you make a thing out of it and stuff. And yeah, is this going well for people at home? Probably. Eh? I don't really, whatever. Eh? Yeah, this is good stuff. But I have one called I Have No Brighter Clever Friends, People Stupid. And I'll do that later for you once the time comes. But like I2, H2, N2, O2, F2, Cl2, Br2, right? P4, bingo. Oh no, wait, that's B4. Oh, come on. That's good. P4, bingo. But you probably don't play bingo anymore. Am I still recording? Probably, eh? Whatever, I don't care. Deal with it, people at home. P4, S8, right? So those are what we call molecular elements. One time people referred to them as diatomic elements. Di means two, but we don't really like that because, of course, P4, S8. There's actually one called ozone as well, which we don't usually talk about because ozone very high in the atmosphere, of course, and that's O3. That would be another example of molecular elements, but it's not one of the common ones we usually talk about because we usually don't, we don't really use that one a lot. So, but that's what we're talking about. Molecular elements, basically molecules that come from a couple elements that are joined together. Okay, same element. If you're going to mix different elements, of course, that's called compounds. That's different. Okay, but anyway, most elements exist as individual atoms. Like I said, magnesium, carbon, sodium. Salt elements exist as the molecular elements, and they are right there. And again, some of you know that as Hofbrinkel. Some of you will know that as Hofbrinkel only takes care of, doesn't take care of P4 and S8. Mine does, that's why I like mine better. Plus mine's catchy. I have no brighter, clever friends. People stupid. Catchy. And sometimes true. And now you're looking over at your friend right now, thinking, case in point. Okay, so I have a question. Here's a review question for you. Why, when you're walking down the street, magnesium is by itself, that's fine, whatever. But you're walking down the street and you come across, I don't know, like say, any of those, nitrogen, oxygen, fluorine. Why do they come in twos? Let's just say P4 and SA. We're going to skip. Well, they do, but I don't really. That's a little bit more complex, but the same reasons. But why does H2, N2, O2, F2? Why do you find them in twos? Why? You know this. I know some of you know this. It's been a while maybe, but why do they exist as twos? Why do they come in twos? What are they trying to do? Come on, somebody. I don't want to talk all day. I won't use your name. I promise. Awkward silence. I won't use your name. Because, well, I can, but anyway. Yeah, because they're trying to complete their outside energy level, right? Remember? Electrons, we want to have full outside energy levels. That's a common theme this year, as it is, well, was kind of last year too, but even more so this year. Why do chemicals react together? How do we get table salt, sodium chloride? Well, because sodium's got an extra electron, chlorine's looking for an extra electron, they happen to come together, and it's the perfect match, yes? And sodium says, we're going to learn a little bit more about this, but chlorine says, hey, I want your electron, and sodium says, yeah, you can have it because I'm looking to get rid of, it's kind of like the fifth wheel, when you go on the dating scene, you know what I'm saying? I think I've used this analogy before. You know, when you're the 11th wheel, you're way out there, you know. So you're looking to get, basically the rest of your friends are looking to get rid of you, right? So when you're the 11th wheel, which is what happens in sodium, when you're the 11th electron and you're way out there, right? Chlorine says, hey, I could use an extra friend or whatever, and so chlorine takes that electron and sodium loses it, and they kind of match up, and that's how we get ionic compounds, right? It's no different with even the simplest one, hydrogen. Hydrogen's got one electron, yes? One proton, one electron, and we know that because it's right there. We're going to review that coming up here. One proton, one electron. Well, geez, hydrogen's thinking to himself, well, geez, I wish I had another electron, because if I had another electron, I'd be more stable, yes? And how is it going to get another electron? Well, another hydrogen comes along, because remember, you're not going to just have one hydrogen atom in the air. You're probably going to have another one somewhere. And if they get close enough together, those two atoms get close enough together, they can now share electrons, right? We call that covalent bonding, but it creates that sharing of electrons. So those two atoms start to share electrons now. So hydrogen has one electron, but it also has this other one over here that it kind of brings closer to it. So hydrogen's got this, hydrogen has two, and this hydrogen's sharing those two electrons. So that's how we can become more stable, yes? Group 18 is probably like, you know, obviously the most stable ones. So they're the most stable because they don't react with anything because they have full outside energy levels, right? And that's what every element's trying to become. Every element's trying to become more stable. You know, the Mr. Bachek of the chemistry periodic table. Group 18, stable. That's a joke. Here's what you're going to miss at home if you happen to stay home, which apparently is them. You're going to miss this. No, but I'm saying, like, you're going to miss, like, the eye roll and the come on, like, that's... A neutron walks into a bar, and the bartender says, hey, for you, no charge. All right. Oh, I know. I'm going to say it again tomorrow, because that's the only joke I have. All right. I think that's it for that. Compounds. We're not going to copy all this, but compounds are yeah, I'm recording. Compounds, well, let's see here. I think that's probably good enough. A compound is a pure substance made up of two or more, so it could be more than two elements, chemically joined together. And again, how do they chemically join together? Well, it's all about the electrons. There's going to be gaining and losing. There's going to be sharing, okay? Each type of compound has the different elements joined together in a certain fixed ratio. But that's what compounds are. Oops, sorry. We'll just mention this real quick here, but yeah, so each type of compound has different elements joined together in a certain fixed ratio. Like, we're going to look at why is nitrogen trihydride or NH3? Why is there nitrogen? Why does it typically form with three hydrogens? Like, what makes it? Why is it NH4 or something like that? And so we're going to look at that, and that's the specific shape we're going to look at, and all that good stuff. Okay, we're not going to copy this part, so just be patient here. Things like that. I guess, yeah, you know what? We are going to copy this though, so let's not worry about that. But compounds can be broken apart. Compounds can be broken apart fairly easily by decomposing them. So usually by heating and sometimes by electrolysis, passing electrical current through them. And these are both chemical processes. Okay. So in atom form, of course, it's hard to break elements are the simple basic things, but if we take those elements and we join them together in a compound, we can usually reverse that, okay, by breaking them back apart. Yeah, don't worry about copying, but solution, of course, when we talk about solutions, we usually have a solute and a solvent. The solute is like, well, it could be anything, really, but the solute is usually the solid. So, like, if we're trying to make some salty water, for example, that would be the salt, right? The water would be the solution. We call those aqueous solutions, right? How we have a whole unit 3 on based on that stuff, which we'll talk about. Water is the most common solvent, of course, aqueous solutions. Yeah, okay. In an aqueous solution of copper 2 sulfate is the solute. the solid in that case, and water would be the solvent. Okay, and you can separate those by sometimes evaporation, distillation, etc. Okay, that's it. That's lesson 1.